back here and clear the screen. That was differential equation stuff. Okay, we are recording, and what I want to do is wait until the maximum number of people get in the room before I make all the end of the term announcements. So remind me, are any of you needing to leave early? No, okay. I was going to say, let me know a few minutes before you have to go so I can make sure everybody, the maximum number of people get to hear. Okay. So, again, I apologize because I've said it to y'all, but I'm saying it to the recording now. I did get all the papers graded last night. I got one class completely finished, and I ran out of time, energy, and everything else. So I will be grading like crazy for the rest of my time here, probably. This afternoon, I do have some free time, I think. I've got to check my emails to see if anything's come in, but I had hoped to be taking my class on a field trip today, but yesterday I finally got word from the people I've been trying to contact for 2 weeks, and they said, oh, you can come at 10:30. No, I can't come at 10:30. So I emailed back and said that, so I don't think I'm going to be able to. I had left those messages and gone through the times over and over and over again. You can come at 10:30. No, I can't. Okay. So I haven't heard back from them. So I doubt if we'll be going on the field trip. But if we do, then I won't have much of a chance to get any grading done today. But I'll work over the weekend. And Monday I've got a big chunk of time. And then the rest of the week I'll be grading like crazy. Okay. Now, that said, we'll move on. Any questions on anything we've covered so far? Okay. From what my memory is, we left off at the top of page 151 in chapter 4, vector spaces, and 4.1 is vectors in Rn. Any questions on any of that? Okay? Or what came before that? So let's now look at this. We did say there's a zero vector in Rn. Okay? That zero vector is weird in that it has no magnitude, zero magnitude, and no direction, because how can a zero vector point anywhere? It can't. Okay? So there's a bit of a weird vector, but every dimension space has to have a zero vector, otherwise things don't work. And one of the reasons is the zero vector is the additive identity element. Just like the number 0 is the additive identity element in the real number system. Give me a number, any number. Make one up. Anybody? 8. Okay? Add 0 to 8, and what do you have? 8. Identically the same number. Same thing with the zero vector. Add any vector in Rn, okay? If n has 4 dimensions, then any 4 things that components of that vector, add the zero vector to it, which is 0, 0, 0, 0, and you still get that same vector, this identical vector. So it's the additive identity element. Okay, similarly, the vector minus v, if you had a vector v, say in R4 or any space you want, and you add another vector to it in that same space, it happens to be negative of v. So you've negated every component in v. Well, when you add those together, you get the zero vector, because 7 plus the minus 7 is 0. Negative 3 plus 3 is 0. If you add those together, you get the zero vector, and that's called the additive inverse of v. Minus v is the additive inverse of v. So, I'm not sure why they said that again here. They said it in the previous thing, but the following theorem summarizes several important properties of additive identity and additive inverses in Rn. So, since not all of you have books, I don't guess. Or do you? You do? You do? Okay, all of you do. I won't write these down. I hope the people at home have them. Let's just go. If V is a vector in Rn, that means V has n components. Okay? C be any old scalar. Then the following properties are true. The additive inverse is unique. Additive identity is unique. Okay? Yeah, it's the, if V plus U is equal to V, U's got to be the zero vector. No question about it. No way you can add some vector U to the vector V and still get V unless that U there is all zeros. Every one of them has to be zero, so it's a zero vector in that space with n components. Okay, number two, the additive inverse of V is unique. So if you add V plus U and you get the zero vector from it, every element here must be exactly the opposite of the element here, which makes it negative V. Okay, so that's absolutely unique. Okay, now, if you multiply the number 0 times the vector V, no matter what V is, no matter what, you're going to get the zero vector. No way around it, because you multiply 0 by every component in V. Okay? Also, if you have the scalar C multiplied by the zero vector, you're going to wind up with a zero vector, because C, even this 7,484,000 times 0 times 0 times 0 is all 0. Okay? So that yields the zero vector. Okay. I'm going to write this one out. I probably should have been writing the others out, but I'll write this one out. If CV is equal to the zero vector, okay? Now, that's all we know, that C times V is the zero vector. We don't know what C is, we don't know what V is, but we know what a couple conditions of them are going to be, and what's that? Either, if this is true, this implies that either C is equal to 0, or, and that's the number 0 because that's a scalar, or V is equal to the zero vector. That's a vector 0. Okay? Either one or the other. Now, they both could be true, but one of them's got to be true, because there's no way you're going to get the zero vector otherwise. It's kind of like what we used to call in algebra the zero product principle. Anytime you when you factor, x minus 3 times x minus 4 is equal to 0. Either x got to be 3 or it's got to be 4. I mean, there's just no way around it. Okay. And then the last one, and this is hopefully pretty obvious, the opposite of V is V. Okay. All right. Now, they show a little proof here. Certainly well worth your while to take a look at that. We just don't have a lot of time, so let's move on. I don't remember if I asked, have any of you had physics yet? Not yet? Oh, you have? Okay. You probably use vectors all the time then, right? Okay. So that's what the linear algebra applied is saying. You use them all the time. Okay. Now, top of page 152 is talking about linear combination of vectors. An important problem in the linear algebra involves writing one vector x. Okay, I think I'll go to clean page here. One vector x in terms of as a sum of scalar multiples of other vectors v1 through vn. Okay, you got v1, v2, v3, up to v sub n. Okay? Now, for some set of scalars, c1, c2, c3, up to c sub n. Okay? Now, if that can be done, if vector x can be written as a linear combination of c1, v1, plus c2, v2, plus C3 V3 plus dot 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 plus all the way up to C sub n V sub n, okay? Then vector x is said to be a linear combination of the other set of vectors. Vectors v, okay? I didn't write them all down, but of that set right there, okay? Now, that's sort of esoteric, okay, kind of vague there. Let's actually do one and see if we can understand what it means, okay? Let's let x, I keep getting caught on that, okay? Let's let vector x equal -1, -2, -2. All right. Now, forgive me if I've talked about this before, if sometimes I put an angle bracket there. Because right now, in my Cal 2 class, we're doing vectors there. Same author of the book, and he uses angle brackets for vectors in that book and parentheses in this book. I don't know why. Okay? Now, there's your vector x, sorry. Here is vector u. Vector u is 0, 1, 4. Here's vector v. Okay? It's -1, 1, 2. And here's vector w. And vector w is 3, 1, 2. All right. Now, the question is, all these vectors are in space R3, R superscript 3. That's why they all have 3 components, okay? So you can add them together, and we'll have scalars A, B, and C. These are scalars, okay? Those are real numbers. Now, it says find the scalars A, B, and C such that vector x is equal to A times u plus B times V plus C times W. Find the scalars A, B, and C that make that true. Okay? Well, you can write it out longhand if you want to. -1, -2, -2 is equal to A times 0, 1, 4, if I wrote that right, plus B times -1, 1, 2, plus C times 3, 1, 2. Okay? Okay. Now, you can do it brute force, and it works certainly well. Let's take the first component. Now I'm going to start on the right-hand side and make it the left-hand side. 0 times A is 0, minus B plus 3C, this one plus that one plus that one must equal that one, right? Equal -1, right? You agree? You give me the next line. A plus B plus C equal -2. And give me the third line. 4A plus 2B plus 2C is equal to -2. All right. That is not right. That's a single B in the last one, isn't it? It's not 2B. We want it to be not to be. Okay, right? If I wrote it down right. Now, do we know how to, second? Okay. Do we know how to solve that kind of system of equations? Sure we do. What's one pretty straightforward way to do it? We've come up with tons of other ways, but nothing really beats the first one. What was that? Gauss, or the Gauss-Jordan elimination. And before I even do that, I'm going to mark Jasmine here. Wait, you're in the other class, sorry. Okay, I don't have it with me now, it's down in my office. How long are you here on campus? Okay, I get through with this class at 11:50. Will you still be here then? That's about it. Huh? Okay. Then I have another class, and I think we're only doing a test in there. I had hoped to do a field trip, but when I heard back yesterday, they gave me the wrong time, so I don't know if we're going on a field trip or not. If we do, then I'm not going to be here much at all. But if we don't, I'll be back in my office probably by 1 o'clock easily. So from 1 to 3:30. But at 3:30, I have to leave to go to the Birmingham East Campus. So it'll have to be between 1 and 3:30, and that's if we don't go on the field trip. Okay. Okay. Sorry about that. All right. So you tell me how to set this up as a matrix you're going to solve by Gauss-Jordan elimination.
You want to create a matrix?
Well, do you have a better way? I'll do whatever you tell me to. I thought you said Gauss-Jordan elimination, which usually comes with a matrix. But you could solve for this. You're right. You could do that, but it might be tough. Okay. I'm going to cheat a little bit because I don't have a lot of room. I'm going to switch the first and second equations and write where did that come from? Okay. And write it as a matrix. My first row will then be 1, 1, 1. You tell me.
0.
-2. Okay. Then the next one's going to be 0, -1, 3, -1. The last one's going to be -2. Got it. Okay. Now, I've already accomplished what I wanted at the beginning. I wanted a 1 in the upper left, and that's why I went on and flipped them right there, because I knew that would give me a 1 in the upper left. And I even have the next one done, a 0 below it. What do I need to do to get next?
You want the 4 and the third.
Right. And how do you do that? Got it. Okay, so we were row 3 minus 4 times row 1. Okay, now I'm going to come up here and do that step just because I need all the room I can get. So the top row stays the same, 1, 1, 1, -2. The second row, we're not messing with that. Now, I am going to mess with it because I know what I want to happen next, right? I want that to be a 1, so I'm going to flip them. So that will be a 1, -3, 1. You okay for me to do that? Okay, wait just a second. Let me mark Travis here. And at the same time, I did not get all your papers graded last evening. Well, you want to hear my really sad story? Okay, you're going to hear it. Yesterday I thought, I'm going to have 4 hours in the office. I'm going to grade like crazy. Well, I forgot I needed to eat lunch. That didn't take that long. But before I had finished lunch just barely when the first student came in. Needed some tutoring. Okay? Evan's not here. I think that's all she wrote for now. I'll get the rest of them to you as soon as I can. I just Not today. Okay. When you come to turn in your other work, I'll give you those others. I'll also get them out there on Blackboard too. Okay. Now, and then I had students coming by for registry. And I had faculty members coming by to tell me about the planning hearing that they had been, oh, good deal, thank you, that they had been to the previous Tuesday, okay? Yeah, the previous day. So I was just completely swamped. I had to make out 2 finals too. I got those done in between all that. In fact, I was well on the way on the first one before that first student came in, and then I was working just like crazy for the rest of the time. So I did not get any grading done. And last night, by the time I got home, it was late, ate supper, and got 1 class graded. That's all. And that was not this class, it was the first class. Yeah. What's that?
I emailed my paper, but I got, you want me to bring it in to you?
I can, if it came to me, I'll print it off, but I grade what I print off, right? So if it has any errors in it, that if you looked at it and say, whoa, I don't want to turn that in, that's what I'm going to see. So if you're okay with it. If you want to print it out, you can, but I'll if you emailed it to me, I'll check. In fact, before we leave today, have me check and make sure it came in.
I got this weather got my asthma and stuff. It's still acting up.
Okay, I can't hear you.
I said the weather been having my asthma stuff act up for like 2 weeks.
Okay.
So I meant to go print out this morning, but I had my asthma acting up again.
Okay. Okay. So I'll try to catch up as soon as I can. All right, so what we did here, we wrote down the first row, and since I knew what was coming next, I went on and negated the second row. Okay, I'm cheating. Y'all are used to this, right? Okay, now we're working on the 4th row. What's the new element in the 4th row? Row 3 minus 4, row 1. That would be a 0, negative 3, negative 2, okay. What's that last one again? Okay, so negative 2 minus 4 times minus 2 is positive 8, right? Is that 8? I mean 6. Is that right? 6, okay. All right, what do we want to happen next? I already did it. A 1 to be a first non-zero element in the second row. So what do we go now? Are you doing Gauss or Gauss-Jordan? Row echelon form or reduced row echelon form? It's up to you. I don't care. I'll do it either way. Help me help. It's usually pretty easy to do Gauss-Jordan, isn't it? Doesn't take that many more steps. So let's do it. So what do we want to happen next? We got a 1 here. What do we want? After that. Okay, above and below, we're doing Gauss-Jordan. We're doing reduced row echelon form. So how do we get this to become a 0? That element right there to become a 0. Using the second row. Second? Yes. Row 1 minus row 2 is the row 2 is the new row 1. Okay, so we're using the second row, so I'm going to write it down. 0, 1, negative 3, 1. Okay? And when you subtract row 1 minus row 2, what do you get? 1, 0, 4, negative 3. Okay. Now, what do we want to happen down below that leading 1? We want that negative 3 to be a 0. How do we make that happen? Exactly. So row 3 plus 3 times row 2. Perfect. What does the first become? 0. Second becomes a 0. The third becomes a -11. You're right. Okay, bad boo hiss there. And then 6 minus 3. No, 6 plus 3 is 9. You're right. That's not looking too good, is it? I think we've done something wrong, because that sure isn't that. I know I was skipping a lot of steps. Let's make sure I wrote it right. 1, 1, 1, -2, 0, -1, 3, -1, 4. Oops! Whoops! I think what you said was right, and I must have botched it up here. Let's do that third equation. 4, right here, okay, 4a plus 2b, I think that's what you said originally, wasn't it? Plus 2c is equal to -2. I messed it, okay? That's a 2, and where else did that come into play? It came into play there. That would make, let's go back and change. That's a 2 minus 4 is minus 6. Wait, that doesn't seem right. No, 2 minus 4 is -2. Okay. Okay. Let's just go on and wipe out all these. Okay. All right. That's a -2. 2 minus 4 times row 1. No, that's negative. All right, I'm losing my mind here. Okay. 4 minus that, 2 minus 4 times 1, that's a -2. I don't know where my mind is. Okay, 2 minus, that should be a -2, and then -8. 2 minus 2 plus 8 is 6. Okay, I think we got them right. Now, correction here. Okay, what I'm going to do, because this is a 0, -2, -2, -6, I'm going to make it -1, -1, 3. Is that okay? -1, -1, 3. Now, my completion here is going to be row 3 plus row 2. All right. That should make things a lot better. Row 3 plus row 2 would be 0, 0, -4, and 4. Ha! I'm liking that a lot better. Okay? Now you can either do a Gauss back substitution now, or we can go on and complete the picture. What you want to do? You want to solve for C? Okay, that gives you C equal to -1. Okay? then the previous line will be B minus 3C is equal to 1. But C is a minus 1, so it would be B plus 3 is equal to 1. What would B be? Negative 2. And then the top row says A plus 4 times C, but C is a negative 1, so it would be minus 4 is equal to negative 3. So what would A be? 1. All right, there we have them. A is equal to 1, B is equal to negative 2, C is equal to negative 1. There we have it. Now we have the constants that make this vector a linear combination of the other three vectors. Okay? Now, can you always do that? Not necessarily, because you could wind up with a row of zeros there, and then you have parameters. Okay? But there are many times that you will wind up with a universal, a set of constants that will make that true. Okay. Now, and what you can, and here's how they typically write that, within the x is equal to, and A was 1, so that would be U, B was minus 2 times V, and C was minus W. X is equal to U minus 2V minus W. Okay. That's the linear combination of the other vectors. Now, it says you'll often find it useful to represent the vector U as either a 1 by n row vector, if this is an Rn, or an n by 1 column vector. Okay? Either way, it will work, and then if you're adding or subtracting, you're just doing corresponding values. So I don't know why they say that now, but a vector can be written as a column matrix or a row matrix, which I think we talked about before. Okay, that finishes 4.1. You can do number 1. By the way, calcchat.com has the odd number worked out solutions, so you can certainly check that. Do either 3 or 5 or both, either 7 or 9 or both, any of the odds 11 through 15. Do 17, it's the only one like that. Do any of the odds 19 to 23, and then do either 25 or 27. Do 29. Do 31. Either 33 or 35. Do 37. Any of the odds 39 to 43, and either 45 or 47. Do 49. Then there's a true-false 51, which I assume has worked out solutions at calcchat.com. No, it has an answer at the back. Excuse me. Oh, man. Do 53. Try to do 55. 57 is a proof. 59 is a writing exercise. You can do whatever you want to with those. Believe you can do, and these are proofs, so only if you want to, 61 and or 63. Okay? And 65 is the writing exercise. So let's move on to the new topic. And this is one, and maybe you felt this true on others, but this is one that gets a little more out there. You know, it's a little more something I don't picture well. Okay? So it's what I'm saying, it's harder for me to visualize what they're talking about here. So you really have to use the rules, the principles. Now maybe a lot of this stuff you haven't been able to visualize, but and you just have to go by the principles. It's a safe way to go anything. So let's talk about First thing they're going to do is mention these 10, what they call axioms, or special properties of vector addition and scalar multiplication in any vector space. And we haven't defined what that is, in any Rn. Suitable definitions of addition and scalar multiplication reveal that many mathematical quantities, such as matrices, and of course vectors, but more than that, polynomials, functions, lots of things like this share these 10 properties. So any set of anything that satisfies these properties or axioms is called a vector space, whether it's made up of vectors or not. That vector may be a polynomial, it may be a function, it may be a vector, okay? So the objects in the space are still called vectors, whether it's a polynomial or function or whatever. If it fits the definition of a vector space, which we're about to give, then it can be called a vector. Important to realize the following definition of vector space is precisely that, a definition. You don't need to prove anything, you're simply listing the axioms required for the vector space. That type of definition is called an abstraction, and this is getting to be abstract. I guess that's what I was saying at the beginning. So, let's let V be a set on which two operations, vector addition and scalar multiplication, are defined. If the listed axioms are satisfied for every U, V, and W in that vector space V, and every scalar or real number C and D, then V is called a vector space. So here are the 10 principles. Okay? Again, this is fairly abstract, but hopefully it does make sense. Okay, the first of these. If U and V are in V, so U and V are elements of this thing we're calling a vector space, and I'll just put a W, and there's supposed to be a V. I don't know what's wrong with my pen. Okay. Then, if that's true, and then U plus V is also in V. Now, if you remember, we did this. I'll take that back. So if I'm teaching two classes the same stuff, I think we talked about this in this class. If you have a vector here in the plane and another vector here in the plane, and you added those together, that resultant vector is still in the plane. Okay? So vector addition remains in that space. Now, if these vectors were in space, but both of them could be added, then the sum is in space, because this would be U1 plus V1, U2 plus V2, U3 up to UN plus Vn. That would still be in space. Okay? Now, you don't have to prove these. These are, again, just a definition. That's going to be true. And what that is, closure under addition. Okay? In other words, the addition is closed in a vector space. If you add any two vectors in that space, whether they're polynomials, functions, whatever, that sum is still going to be in the same vector space. Okay? Number 2. U plus V is the same as V plus U. The order in which you add two vectors or polynomials or functions, whatever, is, and this is the commutative property of addition. Okay, just like we've done before. Okay, this is nothing new. 3. When you're adding 3 or more vectors together, U plus V plus W is going to be the same as U plus V plus W. It doesn't matter how you arrange them, they're all going to come out the same. And this is the associative property of addition. Okay? Number 4. V, that vector space, has to have a zero vector. V has a zero vector. And we call that zero with a, they do it bold, I do it with a vector symbol over it. Such that for every u in the vector space, for each u in the vector space, V, then u plus that zero vector has to equal u. If it equals anything else that's not a zero vector, and it may not be in it. The last of your additive properties, if the pen will ever finish writing, there it goes. For every u in V, there is also another vector. For every u in V, there is another vector minus V, okay, I'm sorry, minus U, such that U plus a minus U is equal to what? The zero vector. If you add a number to it, a vector to its opposite, you're going to get the zero vector, which has no magnitude and no direction, but it's still a vector. So here are the ones that deal with multiplication. Okay? First, if you multiply a scalar times any vector in V, this will also be in V. Okay? So just, if this is a vector V and I multiply it by big a number as I want to, it's still going to be in this plane, right? Or in space, or wherever. It's going to be for any vector space. C times V will also be in the vector space. Oh, and by the way, this one was the additive identity element, and this was additive inverse property. Okay? And this is closure, multiplication. It's closure, to write it the same way they did before, of scalar multiplication. If the vector is in that, C times the vector is in the same space. Number 7. If you do C times the sum of two vectors U plus V, that's going to always have to be CU plus CV. If it's not in a vector space. Okay? That's one distributive property. I can't write today for some reason. Okay. That's a distributive property. I call that of scalar multiplication over vector addition. Okay? Another form of that distributive property, if you had two scalars, C plus D, multiplied by the same vector U, that would be CU plus DU. Okay? And that's the distributive property of vector multiplication over scalar addition, if you want to be precise about it. Okay? But it's just another distributive property. Okay? Number 9. I'm running out of room. This is sort of an associative property. C times DU is equal to CD times U. Sort of an associative property of multiplication. The problem is it's pretty restricted. 2 of the 3 have to be scalars, okay? Because we don't know what multiplication of 2 vectors is yet, so we're not going there. This is just 2 of the 3 have to be scalars, the other is a vector, and then it doesn't matter how you associate them, okay? And number 10, if we can fit it on the page, which it doesn't want me to, is this one. 1 times vector u is always going to be vector u, okay? And that's the multiplicative identity element, okay, or property. Okay. They just call it scalar identity. Trying to think that there is something equivalent in vector. I don't recall it right now. It could be though. All right. Now, all 10 of those things have to be true of a thing we're calling a vector space for it to be a vector space. Okay? Now, let's go to example 1. The set of all ordered pairs of real numbers, R2, with standard operation is a vector space. Okay? Set of all ordered pairs of real numbers in R2 is a vector space. Now, I did leave out one phrase there, with standard operations. Now remember, our standard operations are, we'll shorten these a little bit later, but that vector addition is possible and scalar multiplication is possible. If you want to include all those others, they're all included in that, all 10 of those things, all those things work. So standard things. I mean, you can't say that vector, that scalar multiplication now really is c times vector u would be c minus 1 times vector u. No, you can't make up some new rules, which don't work anyway. You have to use a standard form. Okay? Now, here's your vector in R2. That would be, I have to remind myself to write it with parentheses, V1, V2. Two components only because we're in R2. Okay? And let's see if all these things are met in the theorem. Well, let's say back at 4.1 in the last section we did. And you'll see all those things listed back in theorem 4.1. So we know they have to be true. Okay? So let's not, I mean, I don't know really what else to do with that, but it's true because we did that before. Let's move to R2. Set of all ordered n tuples of real numbers in Rn with standard operations is also a vector space. Okay? In theorem 4.2, we went through every one of those. This is back in 4.1. Okay? We did every one of them. So it's got to be a vector space. Okay? Now, we're now going to look at things that we don't think of as vectors. Let's start with, I'm going to start on the clean page here. Goodness, I'm losing it fast. I didn't have much time between, in fact, no time between classes, basically. I was even late getting back up here. So I really just got a sip of something to drink. I should have drunk a little bit more because I am really dry. Let's talk about a vector space of all 2x3 matrices. Okay? The set of all 2x3 matrices. Okay. can that possibly be, and it says with the operations of matrix addition, scalar multiplication is a vector space. Okay? Now, let's just go back to our 10 things there. And let's think. Set of all 2 by 3 matrices. Now, the first one of those is if you have 2 matrices, both have 2 by 3, can you add a 2 by 3 matrix to another 2 by 3 matrix? Yes. And what's the result? A 2 by 3 matrix. So it is in the same space. So that, number one, is met easily. If you add this 2 by 3 matrix to this 2 by 3 matrix, you get the same result as if you added the second one to the first one. Yes, because you add these two, these two, these two, these two, these two, these two, and if you did them these two, it's the same thing. It doesn't matter the order in which you add them. So number 2 is met. If you had 3 2 by 3 matrices, 1, 2, 3, you added this one to the sum of these two, you get the same thing as if you added the sum of these two back. Yes, because you're just adding those elements, okay? Right? Just because you add this plus these two, this one plus these two, this one plus these two. That's the same as adding these two plus that one, these two together. You're just adding the same 3 numbers, and it doesn't matter because numbers are associative. That's all you're adding in those vector spaces and the matrices. That works. Okay? So addition is commutative there. Does this space have a 0 vector? Zero, 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 zero. There it is. This 2 by 3 matrix with all elements of 0, that's it. You take that and add it to any other 2 by 3 matrix, you just get that 2 by 3 matrix, right? And if you took any old 2 by 3 matrix, give me some numbers. 1, 2, 1, 1, 2, 1. Okay, she's real creative. Okay, and you add to that -1, -2, -1, -1, -2, -1. What do you get? The 0 matrix. So yeah, if you add a matrix to its opposite, you're going to get the 0 matrix. So all 5 of the additive ones work. I bet you all 5 of the scalar ones work, or multiplication ones work. If you multiply C times this matrix here, you multiply each element by that C, and is that still in a 2 by 3 matrix? Of course it is. Okay, so it's closed under multiplication. If you added this C to the sum of 2 by 3 matrices, that would be the same as C times this one plus C times that. Work it out, and you'll see those elements stay the same. Okay, so that distributive rule works. If you did C plus D times a 2 by 3 matrix, let's do C times D times that. C plus D times it. Yeah. C plus D times this 2 by 3 matrix here. Okay. Then that C times this matrix plus D times that matrix. Do it element at a time, you'll see they turn out the same thing. Okay? This gets a little harder to picture. And then if you have, this is one I was jumping to, C times D times a 2 by 3 matrix, that would be D times each of those elements. Multiply C, that would be C times D times each of those elements, which would be CD times each of those elements. That works out the same too. And then finally, if you did the number 1 times that 2 by 3 matrix, you get that 2 by 3 matrix, right? So the additive, the multiplicative identity element. Every step of the way works. So guess what? A 2 by 3 matrix can be a vector. Okay? We usually don't think of it that way, but this makes a vector space, right? Okay. Now, example 4. A vector space of all polynomials of degree 2 or less, that is a vector space. Now, here we get a little bit of a nomenclature problem. And it's not really a problem, it's just something you have to sort of get used to. If I can get that to erase. Okay. P2 is a set of all polynomials of this form. Okay, all polynomials of this form. P of x is equal to a2x squared plus b2x, I think. No, they're using a1x. Okay. I was thinking, where are they going with that? I misread it. a1x plus a0. Okay. That's a polynomial of that form, P2. You answer this question to me. Would the number 3 be that in that set of polynomials?
The number 3.
Second?
The number 3.
The number 3, is that in that set of polynomials? Yeah, because A2 could be 0, A1 could be 0, and A0 could be 3. Yeah, that's in that. So it basically is all polynomials of degree 2 and less, including polynomials of degree 0, constants, linear polynomials, or quadratic. Could x cubed be in that? No, because that's not. Okay, so P2 is a set of all polynomials of this form where degree 2 or less. Okay. Now, the question is that a vector space? I don't like going through all 10 of those things, so let's just shorten it a little bit. Would that be closed under addition? If you had one polynomial, a2 x squared plus a1 x squared plus a0, another polynomial, b2 x squared plus b1 x squared plus b0. When you add those two together, are you still a polynomial of degree 2 or less? Absolutely. You may eliminate a degree. If b2 was actually the opposite of a2, then you may wind up with just a linear polynomial, but that's still a polynomial of degree 2 or less. There's no way you could add those two together and get something with x cubed. Okay? Doesn't happen. Okay? So yeah, that is closed under addition. Adding, the order doesn't matter. If you multiply that by a scalar, c, then you get ca2 x squared plus ca1 x plus ca0. That's still a polynomial in A2. Multiplying by a scalar does not change the power at all. Okay. Even if c was 0, you've still got 0. Okay. It doesn't change it can't increase the power, I'll put it that way. Okay. So guess what? The set of all, does that have a 0 vector? Yes, that would be 0, A2 is 0, A1 is 0, and A0 is 0. All 0, so that would be 0, and that is in that space. So it has a 0 vector.
Do you have to write all of that out to get like full credit, or can you just like show like one example of like how that's true?
Okay. Okay. If the example was like this one, let me put it this way. The most likely type of question, is this a vector space? The answer is yes or no. Now, you can do them in your head, you can write them out, you can say, yeah, I think it is. You can do whatever you want to. I'm not going to say, prove to me that this is. That would be a lot of reading and writing. So it would probably just be, is it? Now, the thing is, if you'll notice on every one of these, and this is where it gets bad. Look at example 1. The set of all ordered with standard operations. Example 2, with standard operations. Example 3, with operations of matrix addition and scalar multiplication. In other words, standard operation. Number 4, be a set of polynomials, blah, blah, blah. The sum of these are defined in the usual way. Okay? So as long as things are like they normally are, but if you come up with some weird definition that may or may not work all the time, then you may have a problem. Those you might have to step through and find out if every one of them is met. So I don't know, that probably was way too abstract of an answer for what your question was, but most of the time I'm not going to say, prove this. It's going to be, is this? You answer yes or no. Now, example 5. The vector space of continuous functions. This is from calculus. So let C be let C of negative infinity to infinity be the set of all real valued continuous functions defined on the real number line. All real valued continuous functions. That set consists of all polynomial functions and all other continuous functions. For instance, would sine of x be in that function, in that set? Yeah, sine is continuous. Would tangent of x be in that set? No, tangent is not continuous. Remember, at every half pi it has a huge discontinuity. All your trig functions except sine and cosine have discontinuities. Okay, sine and cosine continuous everywhere. Would an exponential function be in that set? Everywhere. Okay. Would log? I doubt it, because log is not defined at negative numbers or 0. Okay. Would a square root function be? No, because it's only defined for positive or non-negative numbers. Would a cube root function be? Yes, because cube roots and fifth roots and any octave roots are continuous functions everywhere. Okay. Now, here are the main ones you have to show. Okay? That the sum of any two continuous functions is continuous. Yes, that's true from calculus. It's true from everywhere. You add two continuous functions, you're going to get a continuous function. Okay? You can picture that if you want to. The product of a scalar and a continuous function is still continuous. Okay? And then, does it have, is a 0, does that set have a 0 vector? The function 0 is a continuous function, right? 0 everywhere, okay? All real numbers, x is equal to 0, and that's a continuous function, okay? And if you add that to any other function, you're going to get the same function you had. Not going to change it. And if you add any function to its opposite, you're going to get the 0 function. Okay? So yeah, every one of them does come out. Okay? So here's a summary of, they say, important vector spaces. The others may not be so important. But R is basically the set of all real numbers. I picture this as the horizontal axis, so it could be any axis, but it's just any straight line. That's your R, okay? All real numbers. And that's a vector space, okay? R2 is any plane. That xy plane, this plane, that plane, the ceiling plane, the floor plane, any plane is R2, okay? And that is also a vector space. Because you add anything in those vector spaces, you're going to stay in the vector space, that kind of stuff. Okay. R3, that's space. Okay? The whole room. It has X, Y, and a Z component. Any point here is in that space. You add any two of those together, you're going to stay in that space. Multiply by a scalar, you stay in the space. Everything seems to work there. Now, those are the three I can visualize. This next one, I can't. R sub n. But that's a vector space. That's just imagine that you have n dimensions. Imagine the vectors in that would have n components. And you can add any two n component vectors together. You're going to get an n component vector. Multiply a constant times any n component vector, and you're going to get an n component vector. Everything works for Rn. I just can't visualize it. And this is called C of minus infinity to infinity. Okay? That's the set of all continuous functions defined on the real number line. Okay? Set of all continuous functions defined anywhere on the real number line. Now here's another one. C of, I'm sorry, AB. Okay. Now, the set of all continuous functions defined on a finite closed interval. In other words, from -3 to 14, from 3 to 5, from 4 million to 550 million. Any closed interval there. Now, they say that that is an important vector space. Okay? Set of all continuous functions defined on a closed interval. And I guess that, they say it is, it must be. It seems a little bizarre to me that you could add two functions there and you wouldn't be outside the space, but you really aren't. You're adding the functions, not the space. So that's a continuous function. We don't run into that one much. Okay, P is the set of all polynomials, period. Okay, set of all polynomials. Okay, now P sub n is the set of all polynomials with degree less than or equal to n. Okay? Now, mn, okay, is a set of all m by n matrices. And m sub nn is a set of all n by n matrices. These are required to be square, the others can be rectangular. All those are vector spaces. They meet every criteria. So you don't have to go back and prove any of those. They do. They meet those criteria. Okay? And at this point in reading the chapter, if I were you, I'd have a lot of reservations about their next statement. You have seen the versatility of the concept of vector space. No, I haven't. All I've seen so far is, okay, what are you meaning here? How can I see any versatility there? For instance, a vector can be a real number, an n-tuple, a matrix, a polynomial, continuous function, and so on. Here is the question, but what is the purpose of this abstraction, and why bother to define it? And here they say several reasons, but the most important reason applies to efficiency. This means if you can show that it fits all this, you don't have to go back and prove all this stuff again. If you know it's a vector space, then all these things are true. So here's theorem 4.4. I think I'll write this one down. I'm not sure this will make anything any clearer. Okay. Let V be any element in a vector space V. Let vector V be any element in capital V, vector space V. Now notice here, these aren't your traditional vectors. Any vector, that could be a function, it could be a polynomial, it could be anything that works there. And it seems like this is really redundant, let C be any scalar. Okay? Then the following properties are always true. Okay? These four. 0 times V is equal to 0. We've had that before. Why are we doing it again? I don't know. C times 0, the vector 0, is still the vector 0. Okay? We've had that one before. Number 3. If, and we've had this before, if CV is equal to 0, then it must be that either C is equal to 0 or V is equal to the 0 vector, whatever size that needs to be. And then number 4 is that minus 1 times V is equal to minus V. Now that almost seems just crazy to do, but that is. It's the opposite of V. This means multiply each element in V by minus 1, and you get the opposite of V, which that's how we defined it. So it seems like that's sort of a circular argument. And there's a proof here that you can go through and do. And talk about circular arguments, it really seems circular. Okay. Now, they have a linear algebra applied here. That may be worth a read. I really don't get a lot out of reading that application. It's all true, but anyway, well, neither here nor there. Let's look at some sets that are not vector spaces. We've seen an awful lot that are. Now, this is where some of the really abstract and esoteric things come from. Okay, let's start with one that's pretty obvious. The set of integers, do you think that's a vector space or not? You said yes? Okay. If you went through all 10 of those things, you'd find them all true, right? I want to point out one in particular to you. number. Okay, first from the very top of the page, it says for every vector, and this would be integers in this case, those would be integers, and every scalar, parentheses, real number, C and D. Okay? Now think about number 6 down there. If U is an integer, can you multiply any real number by any integer and still have an integer? No, because you can multiply pi by any integer, and you definitely don't have an integer anymore. You're not in Kansas anymore, are you? So no, that would not be 1. You can do it simpler than pi, 1/2, the one they do in the book. 1/2 times an integer is not always an integer, especially if the integer is odd. If it was an even integer, yeah, it is, but that you're not restricted. You use that for any integer. So that's obviously not 1. Okay? Now, the set of second-degree polynomials, is that a vector space? Set of second degree. Now notice I didn't say P2. P2 is the set of all polynomials degree 2 or less. This is saying second degree polynomials.
You mean they'll all be positive, right? Because it's square.
Not positive, but polynomials is what I'm talking about. Okay? Okay. Well, just because the first one is squared, the second one's not squared, it could be negative. The third one's not squared, it could be negative. If those two added together, no, that wouldn't disqualify it. Okay? Here's what would. Multiply by any scalar, as in the, and even simpler than this, the number 0. Do you wind up with a second degree polynomial if you multiply by 0? No. You wind up with a 0 degree, or, 0 degree polynomial. Just 0. In fact, there's no 0 element in that. Second degree polynomials, not second degree or less, but second degree polynomials. Remember how we define the polynomial so that that first coefficient cannot be 0? That throws it out, okay? Because it doesn't have a 0 element to it. Or, another way to do that is the one they did. Let's do P of x is equal to x squared. That's a second degree polynomial, right? Here's another one, Q of x, and that's equal to minus x squared plus x minus 7. Now, let's add these two things together, and what do you get? X minus 7. Is that a second degree polynomial? No. So this isn't closed under addition. So P2, which is degree 2 or less, yes, that is. But the second degree is not. Also, it doesn't have a 0 vector. Okay, by the way. All right, so those would not be vector spaces. Now, let's get back to that thing about under standard conditions. And this, to me, gets really bizarre, if not odd. Let's talk about R2. Okay? Now, we said that is a vector space. That's the set of all ordered pairs of real numbers with standard operations of addition and, but it has a non-standard definition of scalar multiplication. And here's that non-standard. C times x1, x2. Now, what's the standard definition of that? If this is a vector in R2, okay, you multiply C by it, what's your standard means of doing scalar multiplication? What would be the new vector here?
CX1
CX2, right? You just multiply every element by it, right? Now, that's the standard definition of scalar multiplication. Here's another definition you could have. Why would you do it? I have no idea. But C times x1, x2, define that to be CX1, 0. Okay. Now that's a weird definition, but it is a definition. That would be fine. It's a non-standard definition of scalar multiplication. Now, are any of your axioms back there not work now because of this weird definition? Okay. Okay. Certainly this is still in R2. It's closed under addition. Closed on, let's see. Is it closed under scalar multiplication? Oh. Without spending too much time puzzling over, let's just see why. Okay. Oh, yeah, okay. If you go back to your list of 10, that's on page 155, one through 9 work. They work fine. They work like a charm. Weird but true, but look at number 10. If you put 1 is equal to the number C, it would be 1 times x1, x2. That would be x1. 1 times x1 is x1, 0. But that says that 1 times u has to equal u. And that doesn't. Huh?
Why does it equal 0?
That's our new definition of, if you use a non-standard definition of scalar multiplication, and to answer your question why, I don't know. This is just a silly little mental exercise in my mind. Sorry, I shouldn't say that. But if you use a non-standard definition, yeah, it doesn't work here because you do not get the same vector you started with. You get a different vector. And why, I don't know, except they're just showing that's not a vector space, okay? Because by that new non-standard definition, okay? Now, do not be confused, this is the bottom of page 159, do not be confused by the notion, used for scalar multiplication in example 8. In writing C of x1, x2 equals C x1, 0, the scalar multiples of x1, x2 by C is defined to be that in that example. Okay? That's a special dumb definition. Okay? Now, that's all a lot of blah, blah, blah for 4.2, right? So, Homework exercises here, any of the odds 1 through 5, 7 through 11, they're all at calcchat.com. 13, any of the odds 13 to 33, there's a whole bunch of them. 35 is one you can do, it doesn't have anything like that. There's 37s of proof, you can do it or not, or choose not to do it, whichever. 39 is, again, something a little bit like, it's not even like 35, but it stands alone. The mass spring system, which we talked about under the linear algebra applied, and you'll probably find it elsewhere in the book. If you want to do that one, you certainly can. 43 is okay. It's a pretty good exercise to look at. And then true-false number 45. There's actually 3 pieces of that, so you can look at that. 47 is a proof, and that's it. Now, well, we got about 4 minutes. Is that right? 6 minutes. Let me at least just define what a subspace is. Again, this is abstract, esoteric, not real easy to put your fingers on, okay? What do we mean by a subspace? In many applications in linear algebra, vector spaces occur as subspaces of larger spaces, okay? Wow, okay? For instance, you'll see that the solution of a homogeneous system of linear equations in n variables is a subspace of Rn. Okay? Yeah, we'll see that, I'm sure. A non-empty subset of a vector space is a subspace when it is a vector space with the same operation defined as the original vector space. So here is the definition, and again, this is a definition, not something you need to prove, but just a definition. A non-empty, okay, non-empty subset. Now, here's a couple of things about wording. Subset, you can have a big set of things and then use something smaller. That's a subset. For instance, integers are a subset of real numbers, right? Rational numbers are a subset of real numbers. Okay? Integers is a subset of rational numbers. Okay? That doesn't mean they're subspaces. So subset means every element in the subset is in the bigger set. Okay. But what if you had a subset, W, and that W is not necessarily a vector space, it's a subset W of a vector space, and I'll put VS for vector space, and that will be vector space V. It is a subspace, okay? It's a subset, can be a subspace, and here's what makes it that. When W is a vector space, it's a vector space in its own right. Under the operations of addition and scalar multiplication defined in V. Okay, in the original vector space. Okay? Now, for instance, we talked about the set of all polynomials, right? That is a vector space. Okay. We talked about a subset of that, of P2, all polynomials to degree less than 2, less than or equal to 2. That's a subset of that vector space. It's also a subspace because that's a vector space in its own right. But if that subset of V was the set of all second-degree polynomials, that's the subset of V. V is the vector space of all polynomials. W is all second degree polynomials. There's certainly a subset of that, but it's not a subspace because it's not a vector space. We showed that. It wasn't closed under addition. Okay. So therefore, it can be a subset of a vector space and may or may not be a subspace. To be a subspace, it must also be a vector space in its own right, as long as it follows the same rules that they did in the victim. Okay. Now I've eaten most of the time, right? That's just what a subspace is. You can't do much with it, except you've heard the word. Now let's see if my final got copied. I made a special point of doing it. Let me see if I can find it. I can find where I put it. There it is. I think it is. Yeah. All right. This says test 3. It's really test 4. I forgot to change it at the top. The first time I made these out, I tried to combine chapter 1 and chapter 2, and I wound up not being able to. It just took so long to get all that covered. We needed another test, so I split them up, and I forgot to change my. Now, on this, you certainly can do number 1. You can do number 2. You can do number 3. We did one like that today. I think you can do number 4. We didn't specifically do P8, but we talked about what P2 was in any of the subscript. So I think you can do that one. You cannot do number 5. We just introduced it, but you can't. So skip 5. Skip 6. Okay, I don't think you can do any of the rest of those because we didn't get it. So basically your final is very short, 1 through 4. Okay? Now if you want to answer some of the others, if you get them right, they're bonus points. If you don't want to mess with it, if you get them wrong, you leave them blank, nothing's going to take off. If you happen to get them right, you can get bonus points. Sorry that we didn't get more covered. This was rather bizarre. It seemed like, even though we met all the time and stuff, it seemed like we just didn't get as far as I've only once gotten as far as all that, but most of the times I don't. But we got a little short this time. Sorry about that. Now, here's other things I was going to talk with you about. Okay. Now, I don't know if all of you turned in your papers or not. I think you've either sent them to me or turned them in. I don't know. I don't know if you've turned in all the tests. I've still got so much grading to do I can't tell yet. But if you haven't, please get me your paper. You need to get it to me today not to lose points. Okay, but if you get it to me later, you'll just lose some points, but you still don't get a 0 for it. So it's better to get me something than to get a 0. All right, the tests, read those. Okay. If you haven't done, I'm also talking to people not here too. Okay. Now, when do you turn the rest of the stuff in? While I'm here, do any of you going to try to do it today and get it back to me? Probably not. Okay. Yeah, the test. If you want to, you can. Let me just tell you where I'll be the rest of the day. I've got a class starting in fewer than 10 minutes, okay? Now that class, right now, all we have to do is take a test. That's all, the last chapter test. I had hoped to go on a field trip today, but they came back yesterday and said, how about 10:30? I said, no, I can't do 10:30. I'm teaching then, you know. So I don't think we're going to be able to do the field test. I've got to check and see if they've emailed me this morning. I've been in class all morning. So if they have, we might be able to squeeze in that. So, but even if we do, if you want to bring it back, and I'm not on campus, slide it under my door, okay? Now, I guarantee you after 3:30, I will not be on campus because I've got to drive over to the Birmingham East Campus and teach a physics class there. So I will not be on campus after 3:30. If you want to turn it in after 3:30, slide it under my door, okay? I'll pick it up Monday morning. Now my door is my office door, not this classroom door. Okay, does everybody know where my office is? Anyone who doesn't? Do you know where my office is? Not sure? Okay. Really easy to get to. Okay. Go out the door here, hang a left, go down this little half flight of stairs here, and then go almost to the end of the hall. Don't run into the wall. Before you get there, the last door on the left is the stairwell. The one before that is 265. That's my office. Same side that we're on here. We're the last room on this side here. Last room on that side. Down there is my office. Room. It's a mechanical room right next door, and then classroom before. Across from the orientation classroom. You know what that 265, that's my office. So you can leave it, slide it on my door. Anytime you can't find me, slide it on my door. Okay, let me give you where I'm going to be, what I'm going to be doing for the rest of the time. Monday is a regular class day still. I do have 2 classes on Monday. This is not the last day of class. It is for us Tuesday, Thursday, but not for Monday, Wednesday. They still have class on Monday. So I'll be in class from 8 until 10:40, and then 11 until 1:40. Okay? From that time on, I'm free till 6 o'clock. I'm here at least till 6 o'clock every evening. Okay, Tuesday, I'm giving finals. But my first 2 classes, these 2 classes, don't have any finals. You turn them in. So I'll be in my office from 7:45 until 12 noon. At 12 noon, I'm up here giving the final to the class that's waiting in the hall right now. Okay? That will not take even as long as 2 hours. I'm going to give them at least 2 hours to do it. Okay? So that'll be 12 to 2 approximately, probably less than that. Then I'll be back in my office from 2 to 3:30, maybe earlier than 2, but 2 to 3:30 at least. But at 3:30, I head to the Birmingham East Campus, and there I'm in. If you need me there, if that's convenient for you, I'm in the Ethel Hall Health Professions Building and room 103. Okay, if that's more convenient to you, bring me here. I'm there. Today I'm teaching there from 4 to 5:30, but I'm there in the office hours from 5:30 to 6. Tuesday and Thursday of next week, it's all finals. They're bringing in their finals, so I'm there from 4 to 6. Both days. Birmingham East Campus. Okay? So that's Tuesday. Wednesday, I'm here all day long. 7:45 in the morning till 6 in the evening, mostly around my office. Thursday, here from 7:45 until 3:30. At 3:30, I go to Birmingham campus, and I'm there from 4 to 6. School is not open on Friday, just like it's been in June and July, even though that's August, the college is not open. So if you are turning something in Thursday afternoon, I've already left to the Birmingham campus, so it's like I told you, slide that under my door. When I get in Monday morning, I'll get them graded. But grades for us have to be in by noon on Monday. So therefore, I do not want a stack of papers under my door on Monday morning. So please try to get them in. Now, the other thing, student course evaluations have finally been opened up. I think I've asked y'all before, and no one's ever seen it. They hadn't until either late last week or early this week. They finally opened them up. So please do the student course evaluation. Y'all are all transient students. I really value your comments. I won't know who said what, but I want to see how those compare to Lawson students, because I see them fall and spring basically only, and but now I've got a chance to get evaluated by students from other colleges. So please do the student course evaluation. All right, anything else? Any questions? Sorry, the test is going to be so easy. Get over it. Okay. I enjoyed having y'all in class, and I look